screen. Okay, so what we are going to do today is the following. So in the last class, which was uploaded online on Monday, we have done basis, dimension, linearly dependent, independent vectors. So we want to continue this concept and we go one step further and we define something which is called as orthogonal and orthonormal vectors. Okay.
Excuse me, sir.
Yes.
Sir, can I please ask a doubt from the previous class?
Yes.
Sir, actually, I missed to ask in the previous class itself. So, in the online lecture, the YouTube lecture, he told us that every linear function is an affine function. So, sir, shouldn't it be the vice versa? Every affine function is alpha
No,
plus
every
alpha.
linear function is an affine function, because if you take b equal to 0 in that affine function, then it becomes so linear function is an affine function with b is equal to 0. But every affine function is not a linear function, because if you take b not equal to 0, then it's not a linear function, right?
Yes, sir. Yes, sir.
So that's what we mean. So every linear function is an affine function with b is equal to 0. That scalar A transpose x plus b representation, b is actually 0. Does that clear it out?
Yes, sir. Thank you.
Okay.
And sir, in the proof that you asked us to do for that minimum of z, that should be equals to the in the
Ah,
previous
okay.
lecture.
Yeah, 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 yeah.
Sir, in that also the summation of xi that is given. So the xi is itself the norm of two norm of x, right?
No, that proof you write down and you send an email to me with a
Okay, sir.
picture, and I will clarify that proof with you. Okay.
Okay.
So
Thank you.
you can do that, and probably little later I myself am going to do it in the class anyway. I think in least squares, when we introduce least squares, I think I'll do it there anyway. So that time you will see the proof.
Thank you, sir.
But if you want to get something clarified, you send an email to me for that proof. That's fine.
Okay, sir.
Any
Um,
other doubt
excuse,
on linear independence, linear dependence, if you want to get something clear?
sir, are we going to have a clarification for the assignment? Because there are some doubts regarding the assignment.
What is the doubt?
So like the last question for the MNIST data set, right? So
Yeah.
is it to be even programmed, because there are some questions which need to be coded, right?
So what do you think? MNIST without programming, can you do it?
No, sir. Yeah. So because the first question part was just writing down the number of capital N and small n, but I saw that the further questions were. So how do we submit those part of the assignment, sir?
So you write a program, you generate the output of the program, whatever you are asked to generate, like those 20 class representatives and so on and so forth. So those things you generate, you put them nicely in a figure, 4 by 5 block figure or whatever way is possible, and don't make the file size too big, like 20 MB file don't upload, 2 MB file maximum size, you upload a 2 MB file of all the answers together. Okay.
Okay, sir.
So wherever you see you can type the answers in a Word or PDF document, I think you do that. If you are not comfortable typing, then you write by hand and take a photo and submit. But if you write by hand on a piece of paper, take photo, collect all those things together in a file, the size of the file will increase. So we don't want the size to increase. Okay. So as far as possible, don't make a big file, because otherwise there will not be enough space on the server. It will slow down Moodle eventually. So don't upload big files like 10 MB, 20 MB files. That is not required. 2 MB maximum size. Okay.
Okay, sir.
Yeah. Any other clarification on assignment? Okay, then we move on to this.
So will there be a test on Friday?
Can you speak little louder?
Will there be a test on this Friday?
Yes, there will be a test on this Friday. So let's
Hello.
continue with. Yes.
Sir, I'm a research scholar who joined this class today itself. So how do I submit the assignments?
So everything is to be done through Moodle. So you are supposed to have Moodle account. Okay. So in order to get Moodle account, you have to send email to help desk team IIT KGP Moodle help desk team. So I have already sent you that email. So you contact to that email ID saying that you want to get a Moodle account. Once you have Moodle account, I'll enroll you in the course, Moodle course.
Okay, sir. Sir, for the previous assignments that have already been
No, this
given
is
in
the first
past.
assignment. This is the first assignment. Everything that has happened in this course until today morning has been uploaded in the Moodle. So everything that has been shared in the class, everything that has been done so far is there in the Moodle. Okay. So you
Okay,
can
sir.
see all those things in Moodle.
Okay, sir.
Yeah. Okay. So orthogonal vectors. Okay. So a collection of vectors.
Excuse me, sir.
X1, X2 up to Xk is called as orthogonal, or generally it is called as mutually orthogonal if xi xj inner product is 0, or the way we have been writing xi transpose xj is equal to 0 for 1 less equal I not equal j less equal k. Correct. So if you take any two distinct vectors in this collection, then those vectors are perpendicular or orthogonal to each other. Then we will say that the collection is orthogonal or mutually orthogonal. And if further each xi is such that 2 norm of xi is equal to 1, then the collection is called as orthonormal collection. So this is something that is very interesting. So when we have this orthonormal collection, what we can really write down is the following: xi transpose xj is actually equal to 1 if I is equal to j, and this is equal to 0 if I is not equal to 0. So this is something very easy. For 1 less equal I and j less equal k. So you pick any I and j between 1 to k, and if this relationship satisfies between xi and xj, then you will call such collection orthonormal collection. Normal word comes for normalizing the norm of the vector. Okay, so normal in the orthonormal word comes because of normalizing the norm. So we are normalizing the norm by saying that 2 norm of each of the vector should be equal to 1. Where does that come here? It comes here in the first statement. When I is equal to j, you are saying that xi transpose xi is equal to 1. So xi transpose xi is nothing but 2 norm square. So that we have seen. So what are the examples of orthogonal or orthonormal vectors? So the first example of orthonormal vectors is unit vectors. So E1, E2 up to En, all belonging to Rn, is a orthonormal collection. So these unit vectors are really very interesting. EI transpose EJ is equal to 1 for I not, for I equal to J is equal to 0 for I not equal to J. That's the way we had defined these, right? One ith entry 1, all other entries 0 for EI. That's how we had defined it. So they satisfy this property clearly, and because they satisfy this property, we know that this is an orthonormal collection. Very interesting set of vectors. In the previous lecture, you must have seen that they form a basis of Rn, and now we are saying that it's an orthonormal collection also. Okay, so I will give one more example of orthonormal collection in R3. For example, so you can take 1 0 0 1 0 1 by root 2 minus 1 by root 2 and 0 1 by root 2 1 by root 2. So are these three vectors together orthonormal? So this together is an orthonormal collection. Will you be able to check quickly?
Yes, sir.
It's very straightforward, right? So they will form orthonormal collection. So this is another example of orthonormal collection of the vectors. Is this an orthonormal collection?
Yes, sir.
Why so?
No.
No.
No, sir.
So I'm getting both the answers, yes and no. So
The two norm of the first vector is
Orthogonal.
yeah,
It's
so
not.
this is an orthogonal collection. But not orthonormal. So this is only a sort of a pathological case of appearance of 0, right? So this appearance of 0 is a really troublesome part in this collection. So orthonormal collection is sort of getting rid of that 0 vector. So that is what is basically happening. And in general also, some places people will say that orthogonal collection is by default non-zero collection. Some people will understand it by default, some people will define it, will not define it. But for us, we can understand that this 0 vector is going to be a pathological case. You add 0 to any existing orthogonal collection, it will still be orthogonal because inner product of 0 with all other vectors is going to be 0. So that is really not an interesting case to look at, right? So generally we will avoid having 0 in an orthogonal collection. But the way we have defined it, 0 may be allowed, but in orthonormal 0 cannot be allowed because the norm is not equal to 1, right? So the first thing that we will observe is linear independence and orthonormal vectors. That's the first thing we want to understand. So let x1, x2, xk in Rn be an orthonormal collection. So this is an orthonormal collection. So if this is an orthonormal collection, then what do we know? We know that xi transpose xj is equal to 1 for I is equal to j is equal to 0 for I not equal to j. That's the property that is being satisfied by these vectors, right? So we want to check, what do we want to check? Whether x1 up to xk is a linearly independent collection or not. So that's what we want to understand. So any orthonormal collection, whether it is linearly independent collection or not, that's the question we are asking. So what will we do? How will we show this? So we start with the linear combination. So consider this linear combination: beta 1 x1 plus beta 2 x2 plus beta k xk is equal to 0. Okay, so that's the linear combination I consider with. And when will I be able to say that the vectors x1, x2, xk are linearly independent? If all these coefficients beta 1 up to beta k are equal to 0. So what is it that I want to show? Any linear combination of the vectors x1, x2, xk is 0, then you can achieve that 0 as a linear combination of these vectors x1, x2, xk only by choosing these scalars beta 1 up to beta k to be equal to 0. So what do we do? In order to show that, we multiply, so we take inner product of both sides with respect to xj. Okay, so xj transpose of beta 1 x1 plus so on so forth beta k xk is equal to xj transpose into 0. So the right hand side is 0 vector for any j between 1 to up to k. That's what I do. So if I do that, then using the properties of inner product, what do I get? So what do I get? I get beta 1 xj transpose x1 plus beta 2 xj transpose x2 plus so on so forth beta k xj transpose xk is equal to 0. Correct? Because inner product of any vector with 0 vector is scalar 0. So now this vector is, so this equation is you have to understand vector equation, right? So this is a vector equation, and when you take inner product on both sides, this equation becomes a scalar equation, right? This equation becomes scalar equation. I hope you understand that. And now what is the property of xj transpose x1, xj transpose x2? We already have noted that property down here. Unless I is equal to j, the inner product is equal to 0. So this thing is actually beta j xj transpose xj is equal to 0, which means that beta j is equal to 0 because xj transpose xj is equal to 1. Okay, and this is true for any j between 1 to up to k. So this means that all the scalars beta 1, beta 2 up to beta k, they have to be equal to 0, which means that the collection x1 up to xk is a linearly independent collection, or the set is a linearly independent set. So I hope this argument is clear, because this argument I think we'll use 3-4 times in today's lecture. So if there is any doubt, you can ask now, but this is a very important argument. Is this argument clear? Yes.
You said that the vector equation becomes similar when you do inner product on both the sides.
Yeah.
Yeah, so it's a dot product, right?
Yeah.
Okay.
Dot product, inner product, they are all same. It's basically xj transpose xk. That's how you take dot product or inner product. That's what it is.
Okay.
Yeah.
And one more question following that. So
Yeah.
you say that any given set of vectors is linearly independent if and only if their like if it is transformed into any equation form, if and only if their coefficients are 0.
No. What is definition of linear independence? So if you see x1, x2, xn linearly independent or not, so you take this linear combination beta 1 x1 plus beta 2 x2 plus beta k xk and equate it to 0. So if 0, is a linear combination of x1, x2, xk, then the only way in which you can get 0 as a linear combination of x1, x2, xk is that multiply each of these vectors x1, x2, xk by the scalar 0, which implies that beta 1 is equal to beta k, all of these scalars equal to 0. So that is linear independence. So this was discussed in the lecture that is uploaded online. So one entire lecture is based only on linear dependence and independence. So that's what we mean by linear independence. And once we know what is mean by linear independence, I'll start with this equation. Then what is the objective? If I can show all these beta is are equal to 0, then I'll be able to say that x1 up to xk are linearly independent. If I cannot do that, then these x1 up to xk will be linearly dependent.
Sir, so can we say that for an orthonormal set, the k should be less than equal to n? For an orthonormal collection of vectors, k should be less than equal to n.
Yes, k should be less than equal to n in Rn. So you are talking of Rn. So in
Yes,
Rn,
sir,
that
yes.
is, or in general, when you are n is the dimension of the vector space, then in an orthonormal collection in a finite dimensional vector space, that collection size has to be less than or equal to the dimension of the vector space. That's right. So this calculation is clear, I hope. It is just look at this in a in this particular way. So one of the important properties of orthonormal collection is that the vectors are actually perpendicular to each other. So one of the simplest thing to visualize, so for example, if you go to R3, and you consider the unit vectors. Okay, so we were looking at unit vectors example. So you consider E1, E2, E3, three unit vectors in R3. Then you know that from 12th standard physics, what is that E1, E2, E3? That is I cap, J cap, and K cap, right? So the three basic coordinate vectors which are all orthogonal to each other. So I cap is along the x-axis, J cap is along the y-axis, and K cap is along the z-axis, which is like, so you are sitting in a room, you pick one corner as the origin, then one x-axis, one y-axis, and the vertical side is vertical axis is the z-axis. Then along the x-axis you have 1 0 0, along the y-axis you have 0 1 0, and along the z-axis you have 0 0 1, right? So that's the idea. That's how these orthogonal vectors really look like. But the interesting thing is the second example that I have written here, right? Interesting is the second example that I have written here. And how will you be able to visualize this geometrically? So what are the vectors that I am really looking at? I am looking at these three vectors. So 1 0 0 is the first vector. The second vector is 0 1 by root 2 minus 1 by root 2. So the first line you see on this page. And the third vector is 0, 1 by root 2 and 1 by root 2. Now if you see really what is happening here, is pretty clear. So 1 0 0 is along the x-axis, right? So I'm looking at x-axis. And what are the two other vectors? 0, 1 by root 2 minus 1 by root 2, and where are these two vectors? So these two vectors are basically on the yz plane. So if you chose one axis along the ground as x-axis, then one of the walls in your room is actually the yz plane, and in that yz plane, entire yz plane, so you can consider this as your yz plane, and this is your x-axis. The white pencil that you see is the x-axis. So 1 0 0, the vector is here, and on this yz plane, what is happening? You are having two vectors which are drawn perpendicular to each other, right? So those vectors are given by 0 1 by root 2 minus 1 by root 2, and 0 1 by root 2 and 1 by root 2. So the span of the two vectors here is actually the yz plane, and you see every vector in that span is actually perpendicular to 1 0 0. So you choose any vector arbitrarily in this yz plane. Can you imagine that? The vector will be of the type 0 alpha beta. Do you all agree? And that vector 0 alpha beta is always going to be perpendicular to the vector 1 0 0, the x-axis. I hope this is clear to you. And this is true for any orthogonal collection. So this is something that is really very wonderful. So you take any sub collection. So it is not necessary to take these vectors only. You can take any two of these three. The two I chose, it was very easy to visualize what I was going to say. But this is a very interesting advantage of orthonormal vectors rather, that if you have orthonormal vectors, then you can sort of compartmentalize. And that is a very interesting thing, and that's what sort of happens in one of the most celebrated algorithms we'll see very shortly, called as Gram-Schmidt orthonormalization algorithm. So is what I just said clear to all of you? Is there any doubt about what I just said? This is a very important concept, and I really want you to understand it before we move any further. Okay, so if there is no doubt, then we can move further. And linear combination orthonormal vectors. So let x1, x2 up to xk be an orthonormal collection. And let y belong to span of this x1 up to xk. What does that mean? That means that there exist scalars alpha 1 up to alpha k in R such that y is equal to alpha 1 x1 plus alpha 2 x2 plus alpha k xk. Okay, so we are saying that there exists scalars such that this thing will be true, but the problem is how to compute these scalars. So for example, if you have any set, any linearly independent set x1, x2, xk, and a vector y lies in the span of that linearly independent set x1, x2, xk, you can write this statement. And in general, it is really very difficult to compute these scalars, what those scalars might be. It is very difficult to compute. But in case of orthonormal collection, this is not very difficult. And why? Why is this not difficult? Because the same trick will apply that we had applied previously. So in order to compute alpha 1 up to alpha k, what do we have to do? We do a very simple trick. I do xj transpose y. I take inner product with respect to vector xj on both the sides. I'll get alpha 1 xj transpose x1, so on so forth, alpha k xj transpose xk. And now you know, because I am working with an orthonormal collection, xj transpose xj will be equal to 1 and all other xj transpose xi will be equal to 0 when j is not equal to I. So this implies that alpha j is actually equal to xj transpose 1. So this is very interesting. So if you want to know how to...
Can you repeat this part?
So I am saying that a vector y belongs to span of this orthonormal collection. What does that mean to say that vector y belongs to the span of orthonormal collection? There will exist scalars alpha 1 up to alpha k in R such that you can write down y as linear combination of these vectors x1 up to xk. So you can write down y is equal to alpha 1 x1 plus alpha 2 x2 plus alpha k xk. So at this point you have to understand the fact that when I say a vector belongs to the span, I just know that I can write down that vector as a linear combination of the vectors which are defining the span, right? So I can write down y as alpha 1 x1 plus alpha 2 x2 plus alpha k xk. That's the information that I have. But no one tells me how to actually compute those alpha 1, alpha 2 up to alpha k. And in general, it is really very difficult to compute this alpha 1, alpha 2 up to alpha k. If you remember our first or second tutorial class where we were talking about linear span, it really turned out to be very easy for the examples that I discussed to check whether a given vector is in the span of these vectors x1, x2, xk. But in general, it turned out that it's not easy. In fact, it is equivalent to solving a system of linear equations. So this problem is as hard or as simple as solving the system of linear equations. But there is a catch. What is the catch? If the collection x1, x2 up to xk is orthonormal, if the collection is orthonormal, then we can see that alpha j can be computed very easily. What is it that you have to do? If you want to find out the jth coefficient in this expansion alpha j, you take inner product of both the sides of this equation, both the sides of this equation y is equal to alpha 1 x1 up to alpha k xk by xj. Take that inner product, so you'll get xj transpose y is equal to xj transpose into the right hand side, and then use the orthonormality property and conclude that alpha j is actually equal to xj transpose y.
So just one question, that y equal to span of x1 to, is that xk? Like, I am not understanding. Is that xl or xk? Y
X,
belongs to span of x1 to xk, right?
yeah, it is x1 up to xk.
Okay, thank you. It's fine.
Is that okay? So this is something that is a very useful thing, and this has a very important role to play in future. Okay, when we will see how to actually compute a least square solution, this particular property of finding out alpha j is really going to be helpful for us. Okay, and because you can do something like this, people actually in real life situation, when you write a computer program to solve least squares equation, people actually use these type of theories. Okay, so this will give rise to something which is called as Gram-Schmidt orthonormalization process, and if you want to do it numerically very nicely, you will do something which is called as QR decomposition of a matrix. Okay, and when you do that, you actually find out the solution of a linear system of equation in this particular form. So we will look at all those things little later in this course, maybe next week. But right now you have to understand that this calculation is very important, and orthonormality ensures that you can compute these coefficients alpha 1 up to alpha j very easily. Okay, so now as somebody had already pointed out, I will just write down orthonormal basis. So what happens in an orthonormal basis? So in an orthonormal basis, let x1, x2 up to xn in Rn be an orthonormal collection. Then based on somebody's doubt just 5 minutes back, this will imply that this x1 up to xn is a basis with the property that x1 up to xn is an orthonormal set. Correct? And such a set is actually called as orthonormal basis. So this set is called as orthonormal basis. Why is it called orthonormal basis? Because it is a collection of n linearly independent sets in Rn. So if you have collection of n linearly independent sets in Rn, then in the previous class you must have seen that such a collection will span the entire space Rn. What does that mean? It really means that any vector in Rn can be written as a linear combination, in fact a unique linear combination of those vectors. And in addition, what is the important thing that we get here? In addition, the important thing that we get here is that the independent vectors are not only independent, they are orthonormal also. So if the independent vectors on top of it are orthonormal, then it is something like Sone Pe Suhaga, right? Why? Because now when you want to write any vector in Rn as a linear combination of these orthonormal vectors, it's very easy to find out the coefficients in the expansion, right? So the basis expansion, orthonormal basis expansion, the coefficients are given very easily. And once you have those coefficients given very easily, then your job is done, right? So that's why this orthonormal basis is really very important. Orthonormal basis is crucial because it enables us to write down every vector y in Rn very easily as a linear combination of these vectors x1, x2 up to xn. So I'll just write this for emphasizing. So for any vector y in Rn, how can you write down this vector y? This vector y is actually y transpose into x1, x1, y transpose x2 into x2 plus so on so forth, y transpose xn into xn. So this y transpose x1 is actually like your beta 1, this is like your beta 2, this is like your beta n. And that's very easy. So you know that y will be written as a linear combination, unique linear combination of x1, x2 up to xn. But in fact, that unique linear combination, the coefficients beta up to beta n are also very easy to compute. They are nothing but y transpose xi. Beta I is y transpose xi. So this is the usefulness of orthonormal basis. And once this orthonormal basis thing is clear to all of us, then we move on to one of the most important algorithms, which is Gram-Schmidt's orthonormalization. Okay. So what is this Gram-Schmidt orthonormalization algorithm really do? So what have we seen so far? So x1 up to xk. Okay, so I am considering Rn now. Okay, so I'll not write Rn all the time. I'm just saying that I am looking at this vector space Rn. So x1, x2, xk orthonormal set implies x1, x2 up to xk independent set. So I'll be more specific and I'll write linearly independent. So this thing you have all seen today morning. Just now we proved that if you have an orthonormal set, then the set is linearly independent also. The question is the converse true? So is every linearly independent set also an orthonormal set? That's the question we are asking. What is the answer?
No.
Obviously no.
No, sir.
Why is it? Why is it so? It's so because you can provide a counter example. The simple counter example in R3, 1 0 0, 1 1 0 and 1 1 1. Is this set linearly independent? 1 0 0, 1 1 0 and 1 1 1. Is this set linearly independent?
Yes, sir.
Yes,
sir.
but is it
Yes, sir.
orthonormal? No, it is not.
No,
So
sir.
what I'll do is I will restrict myself only to this set. 1 0 0 1 1 0. This set is linearly independent set in R3, but this set is not orthonormal. In fact, the vectors are also not orthogonal to each other, right? So that's what this set really is. But in order to sort of fulfill this inverse question, there is something very interesting that this Gram-Schmidt orthonormalization algorithm is saying. What is this Gram-Schmidt orthonormalization is saying? Gram-Schmidt orthonormalization is saying that if you give me a linearly independent set, then I can construct an orthonormal set out of this linearly independent set, and that orthonormal set will satisfy certain properties, certain very interesting properties that that will be seen here. Okay, so do you understand? So every orthonormal set is a linearly independent set. Very good. But every linearly independent set is not an orthonormal set. Why? The example is given in front of us. So what is it that we desire? At least if every linearly independent set is not an orthonormal set, can I do some manipulations on that linearly independent set to come up with a orthonormal set? Now I don't want to come up with an orthonormal set which is arbitrary. I can always give one orthonormal set arbitrary, but that has to have some connection with this linearly independent set. So what is the connection that this algorithm actually helps us achieve? It says that from x1 you can go to first set q1, then x1 x2 independent set you can go to something which is like q1 q2, so from x1 x2 up to xk we are going to construct q1 q2 up to qk. Okay, x1 x2 xk to q1 q2 up to qk. So this is linearly independent and this is orthonormal. But I will not give you any orthonormal set, arbitrary orthonormal set with k entries. I will not do that. What I will do? I will do it in such a way that I will have span of x1 is same as span of q1. So I'm building it really. Span of x1 is span of q1. Then I will give span of x1 x2 to be same as span of q1 q2. Then I will give span of x1 x2 x3. So I'll construct these q1 q2 q3 in such a way that this span actually matches this span. So I'm going step by step, and eventually what I'm saying is span of x1 up to xk is same as span of q1 up to qk. So do you understand what we are going to do? So we are going to come up with a strategy. So in fact, in the Gram-Schmidt orthogonalization algorithm, that is what is done. Gram-Schmidt orthonormalization procedure comes up with a strategy. It gives you an algorithm to do exactly the same thing. Okay, so you start with x1, then you construct first vector q1 such that x1 and q1 have same span. Then you go to x1 x2, then you construct the vector q2 from q1 and x1 x2 in such a way that span of x1 x2 matches with span of q1 q2, and so on and so forth. You do this all the way up to the kth stage, then you actually have an orthonormal set q1 q2 up to qk, which will have exactly the same span as the linearly independent vectors x1 x2 up to xk. Do you understand what is happening really here? So let us see this example again. So this example 1 0 0 and 1 1 0, these are the two linearly independent vectors. So these linearly independent vectors are given to us, but these linearly independent vectors are such that they will span which set in R3? So the span is a subspace, so it has to be a plane. So which plane these two vectors are spanning?
XY plane.
Correct. They are spanning XY plane. So if you really see, then what is happening in the picture? In the picture, you have this vector 1 0 0. So 1 0 0 is this vector along the x-axis, and the second vector is 1 1 0. So this 1 1 0 vector is here on the xy plane, right? So this vector is given to us. So these two vectors are given to us. Obviously, these two vectors are not orthogonal to each other. But now Gram-Schmidt orthogonalization, what this Gram-Schmidt orthogonalization is doing. So suppose this vector is x1, this vector is x2. Then from x1, you will construct q1, and from x1, x2, you will construct vector q1 and q2. Okay, so from x1 to q1, it is really very easy. X1 is actually equal to 1 0 0. You can take q1 also equal to 1 0 0. Norm of this vector is 1, so you can take q1 to be equal to 1 0 0, and there is no big deal about it. Now the choice of q2 is really very important. Choice of q2 is really very important. Yes.
It was not 100.
Huh?
What we would have done? How would we have manufactured Q1 if X was not Q100?
Yeah, so I will tell in a minute. So next example, I'll show you how to do that. But this example I purposefully took so that you understand what is happening. Just wait for 2-3 minutes. I'll tell what to do. So Q2 now you have to choose. So from where you have to choose Q2? From X1, which is 1 0 0, and from X2, which is 1 1 0. Okay, from these two vectors and Q1, which in this case is actually nothing but x1. So every time that will be the case, so to speak, you will understand it. You have to manufacture q2. And how do you manufacture q2? You manufacture q2 in such a way that span of these vectors x1 and x2 is actually same as span of the vectors q1 and q2. Is that okay? Do you understand what we are supposed to do? So can you just look at this figure and tell me what Q2 should be actually?
0 1 0.
0
Huh? 0 1 0. Q2 actually should be equal to 0 1 0. So if you choose Q2 to be equal to 0 1 0, then what is really happening? What is really happening is x1 and x2 are actually spanning the xy plane. And you have already chosen q1 to be equal to 1 0 0. Then what is the another orthogonal direction to this vector 1 0 0, which will help you span the entire xy plane? So obviously it has to be 0 1 0. Can you take 0 minus 1 0?
Yes, sir.
Yes, sir.
You can take 0
Yes,
minus
sir.
1 0, right? There is no problem in taking 0 minus 1 0. So you can choose another orthogonal vector to q1 such that span of q1 q2 is same as span of x1 x2, and span of x1 is same as span of q1. What is span of x1? Span of x1 is x-axis, span of q1 is also x-axis, right? So that is something that we have done. So geometrically, that is what is happening. So geometrically, you see there is a sequence of subspaces. What is the sequence of subspaces? The sequence of subspaces is span of x1, then span of x1 x2, then span of x1 x2 x3, then span of x1 x2 x3 x4, so on so forth, up to span of x1 x2 x3 up to xk. So you have a sequence of subspaces, and what you are doing in orthonormalization process, Gram-Schmidt orthonormalization process, what you are doing is simple. You look at x1, you look at the subspace spanned by x1, and you find the orthonormal vector in that subspace. So that is q1. So if x is not 1 0 0, but if x is 2 0 0, then what will you say your q1 is?
1 0 0.
Huh?
We'll have to normalize.
You will still say q1 is equal to 1 0 0. You will normalize it, right? So x1 and q1, the relationship is very easy. If your x1 is not of norm 1, then you normalize it and make it norm 1. So once you have norm 1 q1, then your job is done, right? So q1 is in the direction of x1, but it's of unit norm. They will span the same space. Then what do? Then you see what is the space x1 x2. So what is that space x1, x2? You find out q2 appropriately so that q1 to q2, you find out q2 so that q1 is orthogonal to q2 and span of x1, x2 is same as span of q1, q2. Then you go to the x1, x2, x3, x1, x2, x3, x4 and construct q1, q2, q3, q1, q2, q3, q4, so on and so forth, all the way up to q1 up to q1, q1 up to qk. So geometrically it is clear what is happening. And I chose this example of 1, 0, 0 and 1, 1, 0 specifically. There is no need to stick to this. Geometrically, it is easy for us to visualize what is happening in XY plane or YZ plane or XZ plane. But you can have any plane passing through origin, right? So that's the space that I'll work with. So
I have one question.
yes.
Yeah, so when you said that when you don't have 1, 0, 0, like the unit, like the vectors as 1, 0, 0, 1, 1, 0, you normalize it to get to a value like this, right? If I
So you will always see there. So that's what I'm saying. 1, 0, 0, 0, 1, 0, 0, 0, 1. They are not the only orthonormal set in Rn, right? You already saw one example. This is also orthonormal. The example that we saw at the very beginning, the first example on this slide, that is also orthonormal. So you may get something like this. It depends on what vectors x1, x2, xk you have. Based on those vectors x1, x2, xk, you will have corresponding orthonormal vectors. So the first vector x1 is 1, 1, 1 in R3, right? Then what will be q1? Q1 is 1 by root 3, 1 by root 3, 1 by root 3. Do you understand? That will be your q1. Is that okay?
No.
Because see x1, x2, x3, what is the condition? How will you proceed your algorithm with? The way you will proceed your algorithm with is, suppose your x1, so example 2. So in example 2, you take x1 to be equal to 1, 1, 1 and you take x2 to be equal to 1, 1, 0. Okay, these are the two vectors. Now you tell me what is the span of x1 and x2 geometrically? Anybody? Can you tell me geometrically what is span of x1 and x2?
X1 is a line.
No, span of x1 and x2. That's what we are looking at.
It's a plane.
Span of x1. Span of x1 is a line. That's right. So what is that plane? Can you tell me what exactly?
Plane through the line x is equals to y.
5-degree line, a plane.
So plane passing through z-axis and
what is z-axis?
Span of x1 is a line to origin and 1, 1, 1.
Sorry?
Span of x1 is a line through origin and 1, 1, 1.
That is span of x1. I want span of x1 and x2 together.
It's 1, 1, 1. So that the span will be a plane which contains all these.
So what is that plane? Geometrically, tell me. What is that plane?
XY plane.
Huh?
Plane on XY axis.
Hyperplane.
Yes, it is a hyperplane, but what is the property of that hyperplane? The hyperplane is such that it, see, how do you determine a plane in three-dimensional space?
A plane is
You determine
perpendicular to
a
the
plane
YZ
in
plane.
three-dimensional plane. No, now listen. It is not YZ plane. See, it is a plane which passes. So in order to determine a plane, what do you need? In order to determine a plane, you need three distinct points, right? Three distinct points are required in order to tell exactly what plane you are talking of. What are three distinct points you have here? X1, which is 1, 1, 1. X2, which is 1, 1, 0. And what is the third point?
Origin.
Correct, because origin always have to have in the subspace. The span will always contain 0 elements, so origin is the third point. So you are given 3 points. So from these 3 points, whatever plane passes through these 3 points, that is the subspace that we are talking of. And then there is a line in that subspace. So there is a line in that subspace. What is that line? The line is the line which passes through origin and the point 1, 1, 1, right? So origin and 1, 1, 1, that's the line. So that's the first subspace of the whole space we are looking at. So what do we really want to do? We want to find out two orthogonal vectors which will span the plane which passes through 0, 0, 0, 1, 1, 1 and 1, 1, 0. Do you understand what we are really doing? So here, what is the first of the orthonormal vectors? The first of the orthonormal vectors is 1 by root 3, 1 by root 3, 1 by root 3 from x1. And what will be the second vector? Now that second vector seems to be difficult to compute, right? Because in this particular case, in this example that you saw here, it was very easy. You had x1 and x2, you were having xy plane, and in that xy plane, it was very easy to see if the one vector is 1, 0, 0, then what is the orthonormal vector? 0, 1, 0. That's it. Job is done. But here in this example, it looks like it might be little tricky, little difficult.
So 0, 0, 1. 0, 0, 1.
What will you do with 0, 0, 1?
So sir, like it will give the z axis. So this is perpendicular
why
to.
Why do you want z axis?
Sir, if you take the value of x2 as x2 normalized 1 by root 2 and 1 by root 2, then
no, we have to start with x1.
Okay.
If x1 and x2 is what I have as my order, then I want to construct q1 and q2 in such a way that q1 and x1 span is same and x1, x2 and q1, q2 span is same. So first vector x1 has to come from q1 has to come from x1. If this is the x1 that I am given, then I have q1 is equal to 1 by root 3, 1 by root 3, 1 by root 3. And now from x2 and q1 and from x2, x1 and q1, I have to come up with what might be the value of q2. Okay, so that's something that we have to understand. So that's what Gram-Schmidt orthonormalization processes actually help us understand. So what is it really doing is that if you act so geometrically, what it is really helping me to achieve is that if I give you a subspace, this algorithm is actually helping me to find out an orthonormal basis for that subspace. Is that okay? Geometrically, that is what is going to happen. So this x1, x2 actually spans that two-dimensional subspace. So this x1, x2 is actually basis of that subspace. It's not orthogonal though. So what this algorithm is helping me to achieve is an orthonormal basis for that subspace. So that is something that is really very important. So that's what this Gram-Schmidt orthonormalization process is doing. Geometrically, is it clear what is happening?
Yes.
Okay, so that's the geometry and how to achieve what we really want to achieve in geometry through algebra. That's what we will do probably in tomorrow's class. Now it's almost time. So we will see in tomorrow's class how to achieve this. So inner products is really going to come into the picture, because inner products or dot products, what is the usefulness of dot products? The dot products help you define orthogonality of the vector, right? If the two vectors are orthogonal, x and y, then you know that x transpose y is equal to 0. So if x transpose y is not equal to 0, then you know that the vectors are not orthogonal. How to make use of that information, x transpose y, when x and y are not orthogonal? That's what we will see in tomorrow's lecture in that Gram-Schmidt orthogonalization. And once we understand what is really happening there, we will write down the Gram-Schmidt orthogonalization algorithm and some properties of this Gram-Schmidt orthogonalization algorithm. So that's the agenda for tomorrow's class. So tomorrow also I will teach in class, and also I will record a lecture tonight and maybe tomorrow also, and I'll send those lectures for you to view based on matrices. Okay, so this is what we'll do. Yes, any other doubts?
Sir, what will be the syllabus for the class test?
Syllabus for the class test is whatever we have done until today.
I mean, including today's class?
Including today's class, yes.
Sir, in your previous example, where you have where we were able to tell the Q2 without even solving, this like geometrically, it's very easy to visualize that Q1 and Q2 are orthonormal vectors because they're 90-degree, they're perpendicular to each other.
Okay, just before you finish your doubt, I want to say that if you if you want to like sign off from the meeting, I want to talk to all the PhD students. Okay, so all the PhD students, please do not leave the meeting until I finish my talk with you. Okay, all others who don't want to listen to this can leave the meeting now. I will stop the recording, but PhD students, please wait. I want to talk to you. Okay. Yeah, Lavina, please continue.
So it's geometrically quite visible that Q1 and Q2 are basically your orthonormal vectors because they are perpendicular to each other. Q1 is on x-axis and Q2 is on y-axis, a single line. So and it is very easy even like to look at the span that x1 and x2 is in the same span. So if I have Q1 and Q instead of having Q2 0 1 0, I have 0 0 1. Then Q1 and Q2 are still orthonormal, but they are not in the same span. Am I correct?
Correct. That's right. That's right.
That's what I was just. That's what.
Yeah, and if you want to really understand geometry of this example, then the geometry of this example really is saying that you have a plane passing through origin. So in the origin, you have an oblique plane which is passing through like this. Then what are the orthonormal vectors on this plane? So the easiest thing to visualize is that you can draw a circle on this plane, unit circle on this plane, right? So whatever you understand by that unit circle, you draw that unit circle on this plane. And you take perpendicular vectors on those unit circle. Those perpendicular vectors are always going to span this oblique space, right? So two vectors that we will come up with have to be two vectors on this circle, which are orthogonal to each other.
Give a pictorial reference to this. This will really help. Like
picture I cannot draw a three-dimensional picture. So this is something that you have to sit and visualize. No, see, you have to learn to visualize these things on your own rather than looking at some ready-made pictures. If you see the ready-made pictures, you will never be able to imagine. Right now you have an opportunity to imagine what is really happening. So you have an oblique plane, you have whole day today. No, you think of it, you have a oblique plane and you want to find out two orthogonal vectors on that oblique plane. That's it. So you can visualize it. No need to look for ready reference. Okay, try to do it on your own too.
Okay.
Yeah.
Thank you.
Yeah. So others can leave. I want to talk to all the PhD students. Okay.
Sir.